Who knows what year it is? It's the year of the monkey. That's right. Anybody in here a monkey that knows? I'm not. I'm a rat. I like it. Do you know what you are? You're a rat? You dirty rat. Just couldn't resist. Well, anyway, happy Chinese New Year. Although I had already gotten dressed when I remembered, or I would have wore red. Sorry. All right. Friday we started momentum, and actually covered most of the chapter. But now we're going to, let it sink in and do a little more. And most of the day will be some collisions here with this air track as we bounce things and collide them and shoot them apart, see what's happening. So you're going to go, I use this example a lot, but I never asked. Does anybody's parents in here ever ask them, like, so what'd you learn in physics class today? No? Yeah, well. Say your mom did. And you say, yeah, we studied momentum. And she goes, well, what's that? What do you tell her? Good. Inertia in motion. I like that. Well, since that's what I told you, right? Yeah, and that helps me remember the two aspects of how you'd actually calculate momentum. Momentum is directly proportional to what two things? Mass is one, and velocity is the other. It's proportional to mass and velocity. So that's the relationship. We can say that an object possesses momentum. I mean, if it has momentum. If it's moving, it has momentum. But there's the mass for inertia. It's going to resist wanting to change. So the more mass there is, the harder it will be to change its momentum. Just like if a mass has more inertia, something with lots of mass will have more momentum. But now this motion aspect plays in with momentum. The other term was impulse. Less common term in the normal world, non-science world. And how would you define impulse? Good. Change in momentum. Same thing. It's not the same thing as momentum, but it is the same thing as change in momentum. And what brings about that change? A change in velocity would, correct, or a change in mass. A change in velocity is acceleration, good. So we're reasoning it through. And what actually causes that? A force. Goes back to Newton's second law. This is proportional to a force. The bigger the force, the greater the change you can bring about, just like with acceleration. But now we don't just look at the force, we also look at the direction is important. I'm glad you brought that up, because momentum is a vector. Velocity is a vector. I haven't done this before. But in science, they usually put little arrows over them. I mean, that's one way you can remember there are vectors. There's direction associated with it. And since this is. Yeah, that's important. So impulse is I. That is a change in momentum. And that equals force, but not only force. What else? Time. So that's our other guide to thinking for this chapter. Impulse, which is the same thing as a change in momentum, and it's brought about by a force, but acting for a certain amount of time. I'm going to write, this helped me, so hopefully it'll help one of you. To change the motion of an object. A net force must be applied to it. I hope you got that by now. We've been doing that a while. And when we say change in motion, what are we referring to? Because initially, at the beginning of the semester, that could have meant lots of things in people's minds. But if something's going to change its motion, like with inertia, it wants to resist changing its motion, what are we specifically referring to? Right. We have a net force. That's being applied. That's going to cause the change in motion. But what does that mean to change its motion? What's actually happening? Changing out of one state. Changing what, though, out of one state? Something is in one state, and it goes to a different... What are we referring to? What's being changed? Its state of motion. What do you mean by motion? In physics, how do we define motion? It is relative to something else. We've seen that when we had the board or the table, but what is relative to something else? The velocity. Well, I'm glad I brought this back up. A change in motion. We're changing its velocity. Now, everything you guys said was right. I just was trying to be more specific. Something at rest wants to stay at rest. That means its velocity is 0, it stays 0. Something in motion wants to stay in motion. It's going 55 miles an hour. It's going to continue at 55 miles an hour. If we change that motion, its state, overcome its inertia, its resistance to wanting to change that motion, we're talking about changing its velocity. A net force is required to do that, because a change in velocity over a certain amount of time means it's accelerating, speeding up or slowing down, or, as I heard somebody say, changing direction. That's all part of velocity. So this we had before test 1. To change the motion of an object, a net force must be applied to it. And that's all summed up by Newton's second law. Because this acceleration is a change in velocity with time. So if it has that, we're changing its motion. Now, to emphasize, we're not doing much different. To change the momentum of an object. Exert and, anybody want to guess? Very good. If you wanted to say force, you were half right. Because impulse is a force for a certain amount of time. And that causes a change in momentum. So an impulse. Whoops. Oh, yeah. Exert an impulse on it. So our change in momentum is that impulse, which is still a force. Just like before, we applied a force to make a change in motion. Now if we apply an impulse, a force for a given amount of time, we can actually change the momentum. It's a kind of a parallel that I saw early on, and it helped me. If nothing else, I always like when you can relate something to something you've already learned, so it doesn't seem like you're just having to learn more newer stuff. It's essentially the same thing, just applied differently. So maybe that'll help someone. that makes sense, though? So with this, again, reminder that an object does not possess force. An object in and of itself doesn't have force. It doesn't really, it's kind of meaningless in science because a force is only occurs as an interaction between two objects because all forces come in pairs. Force is an influence, but caused by something else. So you don't really possess a force, but you can be pushed on or pulled on. Likewise, you wouldn't say an object possesses impulse. That, when you apply an impulse to something, there again, there's a force, but for a certain amount of time. It's going to cause a change in momentum. You can possess momentum, but it's an impulse that will cause that to change. All right. No, that's after. Almost forgot. Clickers. I got some questions in. See how we're doing. Okay, it's coming up. It's open. There's your info. Give you a chance to log in. And I want you to compare the momentum of two different objects. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Everybody at least had a chance to log in. Okay. 85% with B. Huzzah! You know how to calculate it correctly. For those missing, the momentum of a 200-pound man running at 10 miles an hour. Now, what's this a unit of? Pounds. Weight, which is a force. So first thing, good, you realize that. That's not a mass. Could you find the mass? If you knew the acceleration, or convert that to newtons or something. For the sake of this problem, you don't actually have to do it. Let's just, but I want you to realize it is a force. It's its weight. It's not the mass. But if we divide it by the acceleration of gravity, here's its weight. If you switch these, then you divide by the acceleration due to gravity, you get its mass. We could do that, but it's not necessary. So essentially 200, representing the mass, times the velocity of 10 miles an hour. Whoops. So 200 times 10 is 2,000. That is not the actual momentum, again, because that's not the mass, but it's proportional to that, 2,000. The second object, 2,000 pounds at 1 mile an hour. So again, multiply, it's 2,000. Since their masses will be converted the same because it's the same acceleration due to gravity, Are you with me? I know this is more talking. I could write it out. So it's going to give the same momentum, which is what 85% of you marked. So you picked up on that. But for the 15% of you that didn't, hopefully that'll make sense and help. Absolutely. Yeah, you bet. So the momentum of object 1, we're comparing with the momentum of object 2. So we take the mass of 1 and its velocity, the mass of 2 and its velocity. Good so far? Well, what I'm saying here is the 200 pounds is representative of the first guy's mass. We could figure it out, but it's not necessary. And his velocity is 10 miles an hour. So representative is 2,000 units of momentum, because that's not exactly momentum again. Over here, the mass was 2,000 pounds going at 1 mile an hour, which again is 2,000 units representative of its momentum. So they're going to have the same momentum. It's just to emphasize that, yeah, one's bigger, but it's not moving as fast. And it's the product of mass and velocity that is momentum. So don't be swayed just by how big it is. Speed matters now, too. Does that help, Brenda? Yeah. Anybody else? All right, new one. So it goes yay fast on the Earth. It goes the same speed on the Moon. So how does its momentum compare then? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Bang. Mostly A, some B. I'll just go for it. The A's have it. Why is it? Why do you say it's the same? What about the mass? The mass doesn't change. It's the same. So if the mass is the same on Earth and on the Moon, and so is the velocity, then so is its product, the momentum. What is less on the Moon? The weight. It's the force of gravity, because the acceleration due to gravity on the Moon is 1/6 of that on the Earth. Yes? Maybe in real life the friction would change the velocity, but the problem said it was at the same velocity. So it's a thinking man's question. Okay? All right, hopefully this one will be easier then. Tyler. Is it Tyler? Say it again. Tyson. Oh, that's why I was been trying to learn more names. Looks like I can start counting down. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, there we go. Quadrupled or doubled? How do you find impulse? Force and time. So if you double the force, what happens to the impulse? It doubles. What if you only double the time? It doubles. So if you double both, yeah, the force doubles and the time doubles. So quadrupled was correct. Does that make sense now? What you thinking? Well, thank you for asking. Let's do this. So impulse, which is a change in momentum, brought about by a force for a certain amount of time. Let's double the force. So it's twice F. Would you see that alone would make it twice the impulse? If that's all we did. Because that would be 2 times the original impulse. So now let's also double the time. That will be 4 times that original impulse. Again, just to emphasize, it's force and time. So if you apply a force for twice as strong, you'll get twice the change in momentum. But you could exert the same force, but just do it for twice as long and get twice the change in impulse. If you do both, they both contribute. You get 4 times. One more. And I admit I like this one a lot. Go. Sometimes people get confused. Just picture a car coming in at a certain speed. Well, it can either come to a full stop by hitting a haystack or hitting a stone wall. How will that change in momentum for the two cases compare? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you answer C. Very good. Now, how many of you, honestly, your gut is like, well, wait a minute, I don't want to hit a stone wall. Something's got to be greater there. Even me, there's something about that. I don't want to do that. Something tells me I don't want to do that. Well, that's what we learn in this physics class. Why don't we want to do that? Because according to this, the answer is, well, it's the same change in momentum in both cases. So why would it matter which one we hit? Bingo. Time, stopping faster. Yes, the change in momentum is exactly the same because you had the same mass, the same car. You're coming in from the same speed, you end up at 0. But how do you want to get stopped? Gently in a haystack? Well, relatively gently. Or all at once on a stone wall. So it's that factor of time. The time's going to be shorter hitting the stone wall. So what will be greater? The force. Let me write that. The impulse, the change in momentum is the same. We got that. But if you do it quickly, a small amount of time, You're going to feel a lot of force to do that, to have that same change. But if you extend the time of impact in a haystack, then you don't need to apply as much force. Just do it for longer. And so it won't hurt as much, won't do as much damage. Padding, cushioning. Any questions on that one? All right. So I got some really old marshmallows here, which actually make this demo work better. Two PVC pipes. If I put a marshmallow in here and blow, I can get a dart gun, essentially, blow dart. But I'm going to put one next to my mouth, and I'm going to put the other in the other pipe way on this end. I can put my mouth around both and blow, so in theory I'm applying the same force. What will happen when I blow?
The one at the end of the tube will just fall out?
The one on the end of the tube.
So
this end?
Away from your mouth?
It'll just fall out, and what will the other one do?
The close one will shoot a little bit further.
And why do you say it'll go further? Because I'm applying the same force.
The force is applied for a greater amount of time.
And which one is it applied the time the longest?
The one that's close to your mouth.
Yeah, the one that's in close to my mouth, you can't see, but it's right there. If I blow for, the extended amount of time, then this one's in the pipe for this amount of time. Where this one, it'll feel the force quickly and leave. And so I no longer apply a force to it. It's like tossing the ball up. You got to apply a force on the ball to throw it up, but as soon as it leaves your hand, you no longer apply a force to it. It's just the weight of it due to gravity. So yeah, this one won't fill it for very long. So how will their impulses compare? Greater impulse for this one. Because I'm going to apply the same F, but this one will have a bigger T. So that'll give it a bigger impulse, thus a bigger change in momentum, which we learned will cause it to accelerate. It'll come out faster, which means it should go further, right? Enough talk. Now, you might be thinking, well, I couldn't tell which was which, so we'll do it this way. Okay, this one's right next to my mouth. I missed you, Mark. And this one I'll put right at the very end and try to blow the same. Yeah, kind of wussy. So that can come in handy. Not only does this time matter when you're having collisions. I wouldn't eat it, Mark. Yeah, sure. It doesn't matter just when you're colliding. It can also happen when you're applying forces to things. Anybody marksmen shoot guns in here? And you probably innately then know the difference between a rifle and a handgun. If you make the barrel longer, you can apply that explosive force for a longer amount of time. And it's not always the case. There's many variables, but you can make it come out faster if you have a longer barrel. It works with a cannon up to a point. At some point, if you make this infinitely long, you're going to meet lots of air resistance, and there's a diminishing returns. But basically, yeah, apply that same force for a longer amount of time, and you can have a greater impulse, a greater change in momentum. So somebody mentioned karate chops last time, and so does the textbook. They often, say you're breaking some bricks, and you're, hi-ya! Anybody done it? Broken a board? Just you and me, Tyson. Oh, you did too? Did it hurt? Did you miss the first time? Some people, they kind of wuss out. What did you learn about that? What were some of the techniques? Or you just went for it? Well, what little I know is they want you to kind of go through it. You don't want to stop, because a lot of people, they'll come in, and if you start slowing down so that you stop about the time you hit the board, well, you're not going as fast. So they usually tell you to aim a little past so that you don't slow down unintentionally, so that when you hit the board, you're going faster. Your mass, but the faster you go, the more momentum you can transfer to the board. But you don't see people doing this either, do you? Why? You know, there's follow through, but they don't do that. They often tell you to hit it and then kind of pull back. And that's kind of that idea of bouncing. I hope you don't get in fights, but if you got to hit someone or someone's hitting you, I won't hit you, Mark, but I know you. I know you more. You come in, and if you follow through, you're in contact with him longer. But it's kind of like you have a collision and you just stay put on his head, and in theory his head starts going back too. And you're not applying any more force as long as his head goes with your fist. It's kind of like the splat ball, or the ball that didn't bounce. You just kind of get there and stop. So if you would hit him and then kind of bounce off, it depends on if you're doing it with your muscles or letting his head bounce you off. Bouncing exerts more force. Remember, it takes ideally twice the change in momentum to bounce something. An impulse to stop and an impulse to push it back up. So that's if you're hitting. If you're taking it, you want to give. And we discussed that before when I was hitting that medicine ball. Because if your head gives, like the coffee filter, he can't apply a force as long as your head's moving with it. Of course, you look kind of silly, but who cares? It doesn't hurt as much, I guess. All right. Since we did the last demonstration, I bought this. It's a different fan cart, but it has cooler options. So I'm going to turn it on here, and let's run it for 4 seconds or so. It's going to blow air that way. I guess I didn't level it as well as I had wanted. Let's just... We'll see if that's close enough. All right. So you turn it on. It starts exerting a force that way on the air. So the air pushes it that way. Well, here's a sail. I'm going to put it on. And you know what'll happen, right? You expect it to stay still? Let's turn it on. Minus. If it was perfectly level, we'd be doing better. You didn't see it move much. And we've gone over that one. But here's something fun. You can design sails. You know this, if any of your sailboaters. You can turn them at angles and worry about components. But even without doing that, this sail isn't flat. See how it's curved? I'm just going to turn it around so the cupped portion is facing this direction. And do the exact same thing. Now, that is real. And not just because it's level. You know, even if we make it go faster, blow the fan stronger, you can actually propel yourself. So something else must be going on in this case. Can you guess what? Wonderful. Wonderful. I thought it would take a little longer for the observation. So let's see, we got the cart, we got the fan, and I'll exaggerate like this. So before, this exerted a force on the air, and it pushed the air this way. So the air propelled the cart that way. But that air runs into the sail, which pushes the cart that way. and they canceled. We just did that again first. But if your sail's like this, you still have all that happening. But one more thing's happening. When that air hits the sail, it gets thrown back that way. What pushes it that way? The sail. The sail exerts a force on the air, not only to stop it, but to throw it back. It's like it bounces now. And just like that bouncy ball was able to knock the block over, there's a greater change in momentum there. And if the sail is pushing harder on that air to even throw it back, what's the air do back on the sail? Pushes it. And it's that additional recoiling force that gets it to move. Yes? Yeah, when it's essentially flat. Right. It didn't move, yeah. So when it was like this, it just kind of came and dispersed, stopped. One to one, yeah. Ideally, it would be 2 to 1. Yeah, I used to remember the name of what this is called. They've made some sails. They kind of look like. Let's see if I can draw it. Kind of have a sail like that. Basically, it's kind of like this, but it's curved like in 2 spots, like this. So you can get the air to get flung back. And just from the shape of that design of the sail, they're using this idea of impulse and change in momentum, kind of like the air bouncing off and getting thrown back to help propel it, just like this guy. Let's do it again. So here is the flat side, 1 to 1. Should just kind of stop when it hits it, and they're balanced, so it doesn't go anywhere. Turn the sail around. Additional, throwing some of the air that way, so the air pushes back and propels it this way. Now, just to really blow your mind, if you blow the air fast enough this way, this is slightly curved, and now some of the air starts going around the edges. And you can't actually get it to go that way. We'll discuss that later. But it is momentum again. What you do know, reason through it, is if it's going that way, something's pushing it, which means it must be doing something to the air that way. And it is in essence, but we'll be able to discuss that better after we study fluids. When the air was blowing slower, it was essentially like the big flat wall is all it saw. Just by blowing the air faster, it was able to leak around the edges here and cause a difference. If it's curved, still going that fast, it should still work going that way. But I think that's a kind of a fun application. Let's do some more collisions. That's what all this is for. 10 minutes, touch everything. Last 2 little concepts over here. So this is an air track. It's like a linear air hockey table just to try to eliminate friction or minimize it so we don't have to worry about it. If we take 2 carts and start moving them around, these are the same mass. Let's say this one comes in at a certain velocity. What will happen when they collide?
They'll both bounce.
They bounce. And will they'll both move in opposite directions? All right, let's do it. Boink. Oh, it's dead stop. Boink. Dead stop. This is fun. So they do bounce, but they don't both move. So what's happening? This is where you play this game. If you're totally confused and amazed, conservation of momentum. Total momentum is always conserved. So the momentum before the collision, and I'm going to write it all out in its glory here once, before, after. So before we have the mass of one of them times its velocity, plus the mass of the other one times its velocity. They're the same mass. So that's the total momentum. Initially, is this guy moving? No. So his momentum is, thanks for humoring me, is 0 initially. So initially, in our system, this has all of the momentum. But you do need to remember, you got to, if this guy's moving, you can't forget about him. All right, afterwards, mv1 final plus mv2 final. After the collision, we saw that this one wasn't moving, and he was. So now the second cart got all of that momentum. So we say he transferred all of his momentum to her. And how fast do you think that is going compared to the initial speed? Yeah, it would have to be the same because they're the same mass. Because it's got to be equal. And that worked because they were the same mass. Now your guess was they could bounce off and go in two directions. Now let's see. So we still have the same start, but yours would have been mv1 final, but it would have been that way, right? Vector, so we'd have to say that one's negative, plus mv2 final. And if that was the case, how would the speeds compare? They'd have to be opposite directions. Good. And compared to this initial velocity? Which would be even bigger? This one? Why would this one have to be bigger? To cancel this guy going the other way. So it's like magically we put more energy into the system, which is why it doesn't work that way. In Chapter 7, we can do the exact same thing and show how kinetic energy is conserved, energy of motion. It's conserved also, which is why this can't happen. Let's switch and do a little guy and a big guy. Now what will happen? Let's do it this way. So I'm going to do it. It's going to come in, same idea. And what do you think will happen? Say the bigger one will half as fast as this one. And what will this one do? Stop? Okay. We have predictions. That's always fun. Let's do it again. So he's at rest. So we still initially have, well, almost this. Just the masses are different. Comes in with momentum, all the momentum, boom. Now they both have momentum. So it's like, what are we doing? We're doing little m v plus big M v, but it's not moving initially. Afterwards, we get moving back that way. And this one moves that way. Now we get this case. And watch the velocities. This one clearly picks up speed because it gains some momentum from this one. But watch his speed when he goes backwards. It's coming in this fast, and it goes back slower. Which I hope would make sense because he just transferred some of his momentum to this one. This one gained momentum. This one lost momentum. But what does the total have to still equal? The same momentum as it came in with. Does that make sense? These are called elastic collisions also. Elastic. They bounce off each other. As opposed to inelastic, where they stick together. Kind of like if you tackled someone and you hang on to them. Or the carts stay stuck together. Let's do that one. Oh, before I can do that one, let's do this one, because I have it tied up. There's a spring here, and I've tied them together. I'm going to burn the string, the force holding them together, so the force of the spring will push on it. So you can think of it, this one will push on this one. So you know what happens to this one, right? It's the same force. It's an interaction. So they're going to feel the exact same force on each other, but in opposite directions. They're the same mass. What do you expect to happen? Same speed. They should separate at the same speed. What's the total momentum right now?
0.
What will the total momentum be when they're moving?
0.
It still has to be 0. But that's okay. This one will have mv that way. This will have negative mv that way. And they do look like they're going the same speed because they're the same mass. If this were lighter, what would have happened? Yeah, it would have went faster that way, and this would have went slower that way. But again, the total momentum would still have added up to 0. Because that's what it started out as. The total momentum before has to equal the total momentum after. Got a few more to do here and we'll end. This one is the inelastic. I have some Velcro here. So in theory, when they come together, they'll stick. Unless it happens too quickly, because it's not great Velcro. So there's a spring in there, same mass, same idea. What do you think will happen when they come back together? They'll stick. And will they move one way or that way, this way, or just maybe stay put? Oh! Friction! All right. Then I get to try to do it myself. I'm not perfect. So I tried to make them the same velocity. They come back together, and boom. Too fast, they didn't stick. Roughly the same velocities come in. Really? Boo! Okay, it is Velcro. And I got 2 minutes. Here we go. Boom. Yeah, essentially stops. And one more. 2 different masses. It's going to be inelastic. I'm going to bounce this. This one comes in. What will happen? They're going to stick. Which way will they move? And will they be going faster or slower than this one? Slower. Because it's more mass, so they have to go at less speed. But the total momentum is still the same. I'll write that one on the board next time. All right, have a good day.